Welcome to CS229 Machine Learning. But these are the names that I think actually one of my over the formula from above. Over 100,000. Okay. Oh, and then lastly, to implement Laplace smoothing with this, you would add 1 to the numerator as usual, and then
Welcome to this video on cluster clustering strategies in real-world applications. After watching this video, you will be able to explain the concept of clustering and its various applications. You will learn how to apply k-means clustering to segment customers based on their characteristics. Additionally, you will gain an understanding of the different types of clustering methods, including partition-based, density-based, and hierarchical clustering. Finally, you will be equipped to analyze agglomerative and divisive hierarchical clustering, exploring their distinct approaches to grouping data points. Clustering is a machine learning technique that automatically groups data points into clusters based on similarities. Clustering can be applied exploring their distinct approaches to grouping data points. Clustering is a machine learning technique that automatically groups data points into clusters based on similarities. Clustering can be applied in various scenarios, such as identifying music genres, segmenting user groups, or analyzing market segments. This method can use just one feature or multiple features in data to form meaningful clusters. This dataset includes historical customer features and loan default status. Classification algorithms, being supervised, learn to predict categorical labels from labeled data. Here, based on the labeled historical data, a decision tree model is trained to predict if a new customer will default on a loan. Clustering is like classification, but works with unlabeled data, independently finding patterns to form clusters. Here, a k-means clustering model segments customers with similar characteristics into 3 clusters. Indicated by the blue, light blue, and red rows. The model operates without knowing if a customer has defaulted, as that data is unavailable and not part of its design. In exploratory data analysis, clustering uncovers natural groupings, such as customer segmentation for targeted marketing. Clustering boosts pattern recognition by grouping similar objects and aiding in image segmentation, such as detecting medical abnormalities. Clustering helps anomaly detection by identifying outliers and detecting fraud or equipment malfunctions. In feature engineering, clustering creates new features or reduces dimensionality, improving model performance and interpretability. In data summarization, clustering simplifies data by summarizing it into a small number of representative clusters. Clustering reduces data size by replacing data points with cluster centers, which is useful for image compression. Finally, clustering identifies essential features that distinguish clusters. Partition-based clustering algorithms divide data into non-overlapping groups. The most common method, k-means, identifies k-clusters with minimal variance. These algorithms are efficient and scale well with large data sets. Density-based clustering algorithms create clusters of any shape, making them suitable for irregular clusters and noisy datasets. An example is dbScan algorithm. algorithm. Hierarchical clustering algorithms organize data into a tree of nested clusters, each containing smaller subclusters. This process generates a dendrogram, revealing relationships between clusters. The two main algorithms are agglomerative, which merges clusters, and divisive, which splits them. These algorithms are intuitive and effective for small to mid-sized data sets. This partition-based clustering result uses the make blobs function from scikit-learn, generating 3 color-coded clusters in the scatter plot. Here are 2 clustering results using the make moons function from scikit-learn that generates interlocking half circles. Both use color to distinguish clusters visually. On the left, the partition-based clustering struggles to separate the shapes, partitionating the data along a red curve. In contrast, the density-based clustering successfully separates the shapes but creates an unnecessary third cluster of 3 points. This chart, created by UCLA biologists, presents genetic data from over 900 dogs across 85 breeds and 200 wild gray wolves globally. They analyzed 48,000 genetic markers using molecular techniques. The diagram illustrates hierarchical clustering, grouping animals based on genetic similarities in a tree-like structure where each node represents a cluster of child clusters. There are 2 main strategies for constructing hierarchical clustering trees: divisive and agglomerative. Divisive clustering uses a top-down approach. It starts with all observations in a single root cluster, which is iteratively split into smaller child clusters. Agglomerative clustering employs a bottom-up approach. Each observation begins as an individual cluster, and similar clusters are merged into larger parent clusters. Let's explore the agglomerative hierarchical clustering algorithm, which uses a bottom-up approach. First, select a metric to measure the distance between clusters, such as the distance between their centroids. The process begins by initializing n clusters, with each cluster containing a single data point. Next, a distance matrix is computed, which is an nxn matrix that displays the distances dij between each pair of points I and j. Repeat the following steps until you achieve the desired number of clusters or merge all points into one cluster. Merge the 2 closest clusters based on the selected distance metric. Update the proximity metric with the new distance values. Let's examine the divisive hierarchical clustering algorithm, which takes a top-down approach. Start with the entire data set as one cluster. Partition this cluster into smaller clusters based on similarities or dissimilarities. Continue splitting each cluster into two until a stopping criterion, which is a minimum cluster size, is reached. Imagine you want to group 6 cities in Canada based on their distances from one another. The distance matrix represents the distances between each pair of cities. The algorithm starts with 6 clusters, each representing a city with the first 2 letters of its name. The initial task is identifying which 2 clusters to merge based on a distance measure, like flight distance. Reviewing the distance matrix shows that Montreal and Ottawa are the closest clusters, so they combine into the next parent cluster. As the algorithm progresses, you can visualize the hierarchy of clusters with a dendrogram, as indicated by the red oval. The distance matrix combines the rows and columns for Montreal and Ottawa in the Ottawa-Montreal cluster. The distances to this new cluster are updated and calculated as the midpoint between the 2 cities. Next, look for the closest clusters again. The Ottawa-Montreal and Toronto clusters are the nearest, forming the Toronto-Ottawa-Montreal cluster. As the algorithm progresses, a dendrogram visualizes the hierarchy of clusters, as shown by the red oval. Next, the updated distance matrix shows that Vancouver and Edmonton are the closest. Similarly, the agglomerative algorithm merges clusters into one, completing the dendrogram. In this video, you learned to explain the concept of clustering and its applications, apply k-means clustering Welcome to K-means clustering. After watching this video, you will be able to describe K-means clustering and explain how the K-means algorithm works. You will also be able to discuss how to determine K. K-means is an iterative, centroid-based clustering algorithm that partitions a dataset into similar groups based on the distance between their centroids. K-means divides data into K non-overlapping clusters, where K is a chosen parameter. The K clusters are constructed to have minimal variances around their centroids and maximum dissimilarity between clusters. Let's understand this definition with the help of this chart showing a cluster of data points. At the center of the cluster is the centroid marked with a red X. This is the average position of all points in the cluster. Data points nearest to a centroid are grouped within the same category. A higher K value, or the number of clusters, signifies smaller clusters with greater detail, while a lower K value results in larger clusters with less detail. Let's look at how to use K-means. First, initialize the algorithm. Choose the number of clusters that you would like to partition the feature space into, and randomly select K starting centroid locations. These initial centroids can be data points or other points from the feature space. Next, assign centroids. Iteratively assign points to clusters and update their centroids. First, compute the distance matrix consisting of the distances from each point to each centroid. Then, assign each data point to the cluster with the nearest centroid. Update each cluster centroid as the mean of the cluster's data points. Repeat until the centroid positions stabilize or you reach maximum iterations. The algorithm converges once the centroids stop moving. as the mean of the cluster's data points. Repeat until the centroid position stabilize or you reach maximum iterations. The algorithm converges once the centroids stop moving. Here's an experiment demonstrating how k-means updates centroids and cluster points with each iteration. The demo starts with two unknown classes comprising circular clusters of points in red and blue and two randomly selected initial centroids in gold, each represented by an X and the plus symbol. With each iteration, you can see the centroids getting closer to their final destinations. Iterations 3 and 4 are identical, thus, k-means have already converged by iteration 3. Although the final clustering contains a few mislabeled points, k-means does a good job of separating them. However, k-means each represented by an X already balanced clusters. In this experiment, the unknown classes, indicated by the pair of circular clusters of points in red and blue, differ in their number of points. The red cluster has 200 points, and the blue one has 10. Interestingly, the results in the first iteration is quite good. The centroid updates for the larger cluster stabilize very quickly. However, the smaller cluster's centroid drifts closer to the larger cluster's centroid, and its cluster consumes more and more of the larger cluster's points. K-means assumes that clusters are convex, meaning that any line drawn between 2 points remains within the cluster. The figure here shows a non-convex set of points colored blue. The boundary defined by the blue line segments approximates the boundary of the set of points. The red lines outline what is called the convex hull of the points. The algorithm also assumes that the clusters contain approximately the same number of points. Because statistical variance is sensitive to outliers, k-means can perform poorly in the presence of noise. As a partition-based algorithm, k-means is efficient and scales well to big data. The goal of k-means is to cluster. The figure here shows a non-convex set of points colored blue. The boundary defined by the blue line segments approximates the boundary of the set of points. The red lines outline what is called the convex hull of the points. The algorithm also assumes that the clusters contain approximately the same number of points. Because statistical variance is sensitive to outliers, k-means can perform poorly in the presence of noise. As a partition-based algorithm, k-means is efficient and scales well to big data. The goal of k-means is to minimize the within-cluster variance for all clusters simultaneously. Mathematically, this means a double sum over each cluster, I, and each point, x, within each cluster, ci of the squared distance between x and its cluster centroid, mu I. Here are the results from 3 experiments to illustrate how well k-means performs under different conditions. The 3 scatter plots on the left are from data generated with scikit-learn's make-blob function. The 3 blobs represent 3 different clusters. The difference between the 3 datasets is the standard deviation of each blob, increasing from 1 to 4 to 15. Higher values disperse the blobs and they become visually less distinguishable. On the right are each experiment's k-means clustering results for k equals 3. The red X's indicate the k-means cluster centroids. K-means does not know the classes or colors assigned to the blobs in the input data. The goal of these experiments is for k-means to uncover these 3 classes. As you can see, k-means has distinguished the blobs quite well for standard deviations of 1 and 4. Where the blobs overlap, the resulting clusters have errors. It would be unreasonable to expect any clustering algorithm to untangle blobs where the standard deviation is 15. However, k-means did what was instructed to do and generated 3 clusters anyway. Intuitively, you might expect at most 2 clusters to be found, the core and outlying points. If the input data had 3 class labels as depicted, the 2 features would be incapable of separating them. More features would be needed to accomplish this separation. Observe that, as the standard deviation of the blobs increases, the cluster centroids that k-means finds get closer together. What if k differs from the unknown number of classes in the input data? Here, the experiment is run with k equals 2 clusters for k-means to determine, and 3 blobs with 3 unknown classes are given. For a standard deviation of 1, k-means correctly identifies one blob and merges the other two into one cluster, with its centroid between the two blobs. Similarly, for a standard deviation of 4, k-means identifies one blob and merges most of the other two blobs into one cluster, with its centroid between the two blobs. When the standard deviation is 15, k-means is left with no option and must impose the two clusters onto what looks like indistinguishable data. As the standard deviation of the blobs increases, the cluster centroids that k-means finds get closer together. The two blobs gradually merge into one, and a blob can have only one centroid. When k is too large, k-means returns unacceptable results. How do you find the best value for k when you don't know much about your data? Choosing k is difficult for complex data. When the data is separable, choosing the suitable k is feasible. How do you know whether the data is separable? While obvious in 2 or 3 dimensions, you can't visualize the patterns easily for higher dimensional feature spaces. You can gain some insight by considering scatter plots between pairs of your variables. examples to see whether any of these demonstrate separability. Some heuristic techniques for gauging k-means performance for a given k include silhouette analysis, which measures how similar a data point is to its cluster, known as cohesion, compared to other clusters, known as separation. The elbow method is a plot of the k-means objective function for different numbers of clusters, and the Davies-Bolden index measures each cluster's average similarity ratio, with the cluster most similar. In this video, you learned that k-means is an iterative centroid-based clustering algorithm that partitions a dataset into similar groups based on the distance between their centroids. The k-means clustering algorithm categorizes data points into clusters using a mathematical distance measure from the cluster center. K-means doesn't perform very well on imbalanced clusters and assumes that clusters are convex. The objective of k-means is to minimize the within-cluster variance for all clusters simultaneously. Some heuristic techniques for gauging k-means performance for a given k include silhouette analysis, the elbow method, and the Davies-Bolden index. index measures each cluster's average similarity ratio with the cluster most similar. In this video, you learned that K-means is an iterative centroid-based clustering algorithm that partitions a dataset into similar groups based on the distance between their centroids. The K-means clustering algorithm categorizes data points into clusters using a mathematical distance measure from the cluster center. K-means doesn't perform very well on imbalanced clusters and assumes that clusters are convex. The objective of K-means is to minimize the within-cluster variance for all clusters simultaneously. Some heuristic techniques for gauging K-means performance for a given K include silhouette analysis, the elbow method, and the Davies-Bouldin index.